Welcome back to ECE 442-542. We are talking about performance specifications and control design, and that will be covered in homework number 5, which is not due this coming Monday, but the Monday thereafter on April 2nd. And then the next Monday you will have homework number 6 due, and that precedes exam number 3, which seems like we just had an exam, but exam number 3 is April 11th. And if you're in 542, your deliverable number 1, which is essentially outlining or proposing a project, that's due on the 2nd, which is a week from Monday, on April 2nd. Today what I want to do is, as promised last time, I was hinting at all these different shapes that we might be talking about. So we're maybe a month late or more on one of these shapes, which is hearts. That's different from what the shapes were in the S-plane. In the Z-plane now we are going to be dealing with circles, which we just covered in the last lecture. But this time we want to start there and then see how do we generate hearts and how do we generate angles, and those are consistent with these time domain performance specifications of settling time, percent overshoot, and peak time, or time to peak. We'll then use that information to figure out where does that place some dominant poles, 2 poles in a 2-pole system. And we'll talk about this constraint table. We'll summarize essentially these constraints. We'll then create a desired transfer function. This is what we would like our system to be doing or behaving like based on those performance specifications. That's what this capital T sub C of Z represents. We'll try to illustrate this with MATLAB, and we will look at how we might generate a gridded unit circle so that you can now more effectively translate these performance specifications into locations in the Z-plane. And hopefully that will all be discussed. We will, if time permits, we'll talk a little bit more about sample period, but really you should already know this in terms of sampling frequency, Nyquist frequency, and aliasing. How are those related? We know if we sample at omega sub s, then the Nyquist frequency is half of that. That's the highest frequency that we have, omega sub s over 2. And if we actually are sampling some waveform that's of a higher frequency than that, it will actually get mapped back into DC to omega sub s over 2, and that's what we're meaning by aliasing. It will alias or look like something less than what it actually is because we may not be sampling fast enough, or if we don't low pass filter sufficiently prior to sampling, we may have high frequency signals looking like low frequency signals, and that may mess us up in terms of our design or our control, and we want to try to avoid that. There can be conditions or situations where these performance specifications are not consistent or they're incompatible. Maybe we require 3 performance specifications and they may not all simultaneously be satisfiable. That's what I mean by those performance specifications being incompatible, and we'll try to look at an example of that and how we might modify the performance specifications to make all 3 be satisfied. And we'll talk a little bit about controller design, provide an overview. What's the motivation behind that? And it may turn out that I have to provide these 3 topics sort of off campus and make those available on your own, in terms of I might generate or have already created material covering these, and that might be on your own to work through or to try to understand, because I think you have the skill set to make that happen. And you have plenty of time. I know that you have unlimited time as graduate students, as undergrads. If you're an undergraduate student with a capstone, that just frees up all the time in the world to work on anything that you might want. So, that being said, we'll take that into consideration, but that's one reason why you're in school, is to learn how to organize and optimize your time. Performance specifications. We're continuing that discussion, and this should actually just be a review from last time relative to the settling time performance specification. And with respect to settling time, what do you think about when you hear now settling time in the Z-plane as far as a shape might be concerned? If you hear settling time, what shape should be coming to mind in the Z-plane? You should be thinking circles, concentric circles, bullseye, and if those circles are smaller, what does that mean in terms of settling time? Is your settling time faster for a smaller circle or slower for a smaller circle? It's faster. The closer you get to the origin, the faster the response. And if you get on the origin, then you have a deadbeat response. And we'll talk about that a little bit more. But if you had a second order system that was supposed to have a deadbeat response, then your denominator would be z squared. You would have two poles at the origin. You would want both of your poles right at the origin if you wanted a deadbeat response for a second order system. In this case, for the performance specification, if you're given the settling time, and you might be given that in units of seconds or some other units of time, or it might be specified in terms of number of samples. Either of those two you should be able to work with. If you're given that condition in absolute time, hopefully you now have the sample period, and with the sample period you can now determine what the number of sample periods should equal. And once you have T settle, then we derived last time how to translate that into what that corresponds to in terms of length of time, number of sample periods, or I'm sorry, what the radius is to produce that particular settling time. Here we have r to the n equaling 0.01 for our 1% settling time. That's the relationship that we end up with. If we take the log base 10 of both sides, that gets rid of that n in the exponent, or it moves it around. It doesn't get rid of it, but it removes our exponent. And now we can solve for capital N sub s, or the radius, and in this case, if we're given N sub s, we'll solve for r. And to solve for r, we can take the anti-log of that and produce our radius of this set of complex poles in the z-plane. They are now going to be this distance away from the origin in the z-plane, dependent on what capital N sub s, or the number of sample periods, are equal to. In this case, the thinking is, what kind of r results if N sub s is small? And here I'm really sort of saying, is r smaller or is r bigger if N sub s is small? And a small value of N sub s could be 1. Just pick an extreme value. N sub s could be 1 sample. We now have 10 to the minus 1, I'm sorry, 10 to the minus 2 divided by 1, or 10 to the minus 2, or 1 over 10 squared, or 1 over 100. R is how big if we have 1 over 100? 0.01, right? 10 to the minus 2. So that's pretty small. Or if N sub s is small, what happens to R? If we want the settling time to be really tiny, short, if n sub s is one sample period, how small should our radius be? It's really small, isn't it? So a small settling time, n sub s small, implies that our radius r is smaller than if we had n sub s large. If we had, and here you could think, here we have 10 to the minus 2 over n sub s, or you could just say 1 over 10 to the 2 over n sub s. If we plug in a large value of n sub s, maybe we'll show what it is for 60. If we made n sub s 100, then we have 10 raised to the 10 over 100. I'm sorry, 1 over 10 raised to the 2 over 100, which is 1 over 10 to the 150th. That's not a very large exponent. That's getting close to 0. And 10 to the 0 is 1. So we're a little bit bigger than 1. 1 divided by something a little bit bigger than 1 is going to be very large relative to the unit circle. It's going to be just inside the unit circle. Here then, for n sub s large, relative, r is going to be larger. As an example, suppose somebody says, I want the settling time to amount to 60 sample periods, 60 samples. You can now plug in that 60 in the appropriate location in the exponent. You now have 1 over 10 raised to the 1 over 30, and 1 over 30 is not very big. So we have 1 over something a little bit bigger than 1, and that now gives us a radius of 0.926. So that now tells us how far these complex poles are away from the origin in the z-plane for this specification of having a pretty long settling time. We want to settle in 60 samples. And you could plug in a particular sample period. If your sample period was 100 milliseconds, or 0.1, then that means that in 6 seconds, you would be settled. If you're settled in 6 seconds with this sample period of 0.1, then you want your poles to be at 0.926. The poles could be exactly in the same location with a much smaller sampling period, and that produces a much faster a much faster settling time of 600 milliseconds. So what the poles represent is obviously going to depend on the sample period. That's one thing to take away from this little example of 2 different options for the settling time, capital T. If we simply say, oh, what's our settling time in number of samples, capital N sub s, you can then figure out what the radius needs to be for that value of number of samples for settling time. We can also work this settling time in the other direction. If somebody now gives you 2 complex poles and they say, how many samples is it going to take to settle, to reach a 1% settling time, now we're really wanting to use this star equation, base 10 log of r equaling minus 2 over n sub s. We now want to solve that for n sub s. We can now, given r, find what the number of sample periods are equal to. In this case, if we solve for n sub s, it's going to be minus 2 over log base 10 of r. But is that really going to give us maybe an integer value, what's on the right? Log of r base 10 may not give us an integer when we divide it into 2. And so what I'm going to do now is simply put a ceiling function on that. which means if the result ends up being 10.7, now my number of samples is going to be the smallest integer larger than 10.7. It'll be 11 samples that I'm going to expect my result to be finished settling by. So this is now the smallest or the least integer greater than or equal to the argument of that ceiling function. Suppose somebody hands you a couple of complex poles and they are a distance of r 0.8 away from the origin. Now you want to know what's the settling time, how many sample periods will it take for this particular set of poles. All we have to do is plug into that formula. N sub s is now minus 2 over log base 10 of 0.8. And log base 10 of something less than 1 is going to be negative. We have minus 0.09691. Or almost 0.1. Something a little bit bigger than 20. So now we need 21 sample periods to reach our 1% settling. Yes?
Do you have like multiple R's? Do you choose the biggest one for settling time, like because it's the slowest?
So now the question was, if you have multiple poles, what have we agreed to do in this particular class? If I had now 4 poles, and maybe those 4 poles were in 2 pairs of complex poles, what do I do? Now I don't have just 2 poles. So now we've agreed in this class to just use the largest radius. That determines our settling time. So we use the poles that are associated with the largest radius. If we ended up with 4 real poles, we would use the pole that's closest to 1 on the real line to determine this R. That would be our R. If we had a couple of reals and a couple of complex, we would just compare all those R's and we would pick the biggest R. Yes?
If R was greater than 1 and you asked that, would we just say it's a true question? It doesn't settle? Or?
So, are you asking a question or are you telling me an answer? So the question was, what happens when a pole is outside the unit circle? And the follow-up to that question was the answer. They said, is it a trick question? And I'm not sure it's a trick question, but you gave the right answer. You said it doesn't settle. It's going unbounded. If we have any pole outside the unit circle, that's going to go unbounded, and so we really can't talk about a settling time because that mode is going to get excited, and if it gets excited, then it's going unbounded. And the others could all be well behaved, but all it takes is one pole outside the unit circle and it messes everything up. Is that clear? That's then our first performance specification. If we're interested in settling time, then we can go either way. Somebody can give us t-settle, and that means that we need to find an R, which is a circle, or if somebody gives us the poles, we can find their R and tell them what the settling time is, either in absolute, in seconds, or in number of samples. We will compute it in number of samples, and then we would have to be told or have available the sample period to translate it into absolute time. If we don't have a sampling time specified, we could only say how many samples it's going to take to get us to 1% settling time. There's one shape, circles, and it's associated with the first performance specification that we've talked about. Let's now look at the second performance specification, which is related to percent overshoot. And many times I'll just abbreviate that as PO. If somebody gives us a percent overshoot, and that's how far over where we want to end up, or where we do end up in our step response, we find that percentage, max minus final divided by final times 100%. That's the percent overshoot if you're looking at it from data. That will actually give us a zeta value, a damping ratio. And we have this relationship that corresponds to or provides the damping ratio zeta, and zeta is what kind of a range of numbers are we looking at for zeta? Do you remember? 0 to 1. And if zeta is 0 in the S-plane, where are your closed loop poles? Do you remember? If you have 0 damping, if your damping ratio is 0 in the S-plane, where are your poles? It's on the imaginary axis, isn't it? If it's no damping, you're just sitting there shaking, aren't you? It's just an oscillation. No, it's not the origin. If it was at the origin, what would the frequency be? I mean, it could be at the origin if zeta is equal to 0. You have a DC signal if you're at the origin in the S-plane. If you're the origin in the Z-plane, you're very fast.
So there is no real value to it.
For zeta, zeta is going to live between 0 and 1, and it will be a real number. And it's a damping ratio. So that gives us, in the S-plane, it's the ratio of the real part of our complex pole divided by the hypotenuse of that complex pole. If we now are given percent overshoot, here's the formula that we can use to calculate what that zeta value is. And this zeta value in the S-plane gives us this wedge relative to our complex pole location. And what you don't want to forget is that 1/2. You want to take the square root of that eventual ratio. So if somebody gives you percent overshoot, 10%, you would plug in 10 for PO. So PO divided by 100 is 0.1. Let's now look at this scenario as far as what zeta looks like in the Z-plane, maybe based on what's happening in the S-plane. What happens, or what do you have if I say I fixed a zeta value in the S-plane? What does that correspond to in the S-plane? Pardon? This is an angle, isn't it? And it's consistent with this angle theta. And a nice angle theta in the S-plane that we talked about last time was 45 degrees, or a zeta value of 0.707. So there's our zeta value in the S-plane. In the Z-plane, what we are going to see is the following. I'm going to try to draw these and then explain where these come from after I draw them. If zeta is equal to 0, what do we end up with in the Z-plane? If zeta is equal to 0, where are we in the S-plane with zeta equal to 0? You just told me. You were right here, aren't we? So if this was our omega sub n, then there would be zeta equal to 0. And if we had the same omega sub n, there is where we would be critically damped. That would be zeta equal to 1. Question? So theta is 90 degrees for zeta equal to 0. Theta equal 90 degrees is zeta equals 0. Did I say that right? Zeta equals 0 is theta equal 90 degrees. Theta equal to 0 is zeta equal to 1. Let me sketch or try to sketch what this looks like in the Z-plane. But first, to give me something to go on, if I now sketched a shape in the Z-plane with zeta equal to 0, what would I sketch? For different values of omega. So now I'm saying, what happens if I sketch or translate this imaginary axis into the Z-plane? What's the imaginary axis mapped into the Z-plane? That's the unit circle. So zeta equal to 0 maps into the unit circle in the Z-plane. And what happens as we increase zeta, we end up with actually logarithmic spirals in the Z-plane. And I'm sort of taking liberty with that shape and calling it a heart. The logarithmic spiral will look something like the following. That should be starting at the 1. And this might represent This is a sketch, but that's zeta of 0.2. Zeta of 0.9. And where do you think zeta equal to 1 is? It's now on the real line, isn't it? Zeta equal to 1 is right on the real axis in the Z-plane. So if you use your imagination, do you see if you stuck a mirror on that Z-plane on the real line and you mirror imaged that shape down below, which is what you have, do you sort of see a squished heart depending on what the zeta value is? Use your imagination, but it kind of looks like a heart if you just put it over. So that's the heart shape due to percent overshoot. Let's now see how that might become a heart shape, or where do these logarithmic spirals come from? Looking at the S-plane, cosine of theta, if we said that this particular value, let's say that this was omega sub n, that real distance was zeta omega sub n. So the cosine of that angle theta is adjacent over hypotenuse. And the adjacent is the real length, that's zeta omega sub n, over the hypotenuse, which is omega sub n. Or that's now zeta. You can now inverse cosine that equation and end up with an equation for theta. If somebody gives you a zeta value, you can now find what the theta is. If I give you a zeta of 0.7, that's going to map to 45 degrees, approximately. That's in the S-plane. That's the S-plane angle. Let's now use that information to look at what Z is when we map that S into the Z-plane. The way that we've parameterized S is now to be at minus sigma, but sigma was zeta omega sub n, plus j omega sub n square root of 1 minus zeta squared times t. And if we distribute that t among the two parts of that exponent, and we separate the expression using the two exponential pieces into two terms, we can now say that that's e to the minus zeta omega sub n t, e to the j omega sub n t square root of 1 minus zeta squared. Where this piece is r, and this we might actually, well, let's just do the whole thing. This is e to the j theta sub d. Let's see what happens to r, the distance away from the origin in the z-plane, and theta sub d for different for a fixed value of zeta. We want to see where do these logarithmic spirals, how do they get produced? And we said that those are existing for a fixed value of zeta. R1. Let's say that now we pick an omega 1 right here. Let's say that this is now omega sub n1. Not that far from the origin. Then we would have R1 is e to the minus zeta omega sub n1 cap t. Let's keep cap t fixed. Suppose now we look at R sub 2. E to the minus zeta omega sub n2 t. And maybe omega sub n2 is there, bigger, further away. So our natural frequency is increasing. Let's pick one more, R sub 3. E to the minus zeta omega sub n sub 3 t. Where now maybe omega sub n sub 3 is there. Again, we said we're fixing zeta, so we're staying with the same angle in the S-plane. And what does that correspond to when we map that into the radial distance away from the origin in the Z-plane? What's happening in the direction that I've indicated that red arrow? What's happening to our omegas? Are they getting bigger or smaller? The way that we define them. This is now larger, so that arrow is pointing to increasing natural frequency. If t is fixed, capital T, the sample period is fixed, and if zeta is fixed, what happens to our r's in this same direction? We're now getting bigger exponents, aren't we? But those exponents are with a negative sign. So we now are getting a bigger negative exponent as we go down, and so the r's are decreasing. That means if we fix zeta and we increase omega sub n, somehow the radius is shrinking as we keep getting omega sub n bigger. Let's now look at the angle theta sub d for those same changes in omega sub n. Now this is a little different, but now we have theta d1 is now omega sub n1 t square root of 1 minus zeta squared. Theta sub d2 is omega sub n2 t square root of 1 minus zeta squared. And theta sub d sub 3 what happens to the theta as we increase the omegas? T, capital T, and the zeta are fixed. So that t square root of 1 minus zeta squared, that's a constant. Now we're just increasing the omega sub n, so as we go down in our thetas from top to bottom, what happens to the theta? Those increase. So now we have increasing theta sub d. Did I hear a question? So theta sub d is now in the z-plane. So now we have, if we look at this, if we look over here and we fixed zeta, capital T is the same. Now as we increase omega sub d, the natural frequency, do you see that simultaneously we have the angle getting bigger and the radius collapsing? And that's where these logarithmic spirals come into. So as we walk along these logarithmic spiral curves, the radius is getting shorter and the angle theta sub d is getting bigger. In this particular plot, there's the r, and that's theta sub d. And as r is shrinking, theta sub d is getting bigger. And that's what's producing these logarithmic spirals for a fixed zeta. So when we talk about percent overshoot, that means we're talking about a zeta value. And if we're talking zetas, you want to be thinking hearts in the z-plane, these logarithmic spirals in the z-plane. And I guess it was appropriate that I was using red for hearts. So hopefully you're color coding your lectures. Now let's just look at, now that we have two performance specifications, what happens if somebody combines those? We have settling time and percent overshoot. So I might call those performance specifications. I might call them design specifications. Whatever they are called, let's see what happens. Suppose that now we're given a settling time and a percent overshoot. Now what are we given? What does T settle give us? What shape? Circle. So now we have T settle leads to an R, and the percent overshoot leads to what? A zeta, right? That damping ratio. So here we have hearts. Have hearts on the brain. We have circles here, and the percent overshoot is hearts. And so what we're looking to do is figure out, for a given settle and percent overshoot, can we now overlay these and have some intersection happening so that we're at a certain radius away at a given zeta value. We now want to know, where are the poles located? If we're given settling time and percent overshoot, we're effectively given the radius and the damping ratio. We want to find Z delta, which is R e to the j theta sub d. But this now really hasn't explicitly given us theta sub d. It's given it to us indirectly. If we could now sketch these curves very accurately on our engineering tablet, we could draw the circle and we could draw the zeta curve, the logarithmic spiral, good luck, and now you could pinpoint where those intersect, and that would be your Z delta. But we have the formulas such that we can actually create an expression that will express theta sub d in terms of R and zeta. And then we can calculate what that theta sub d needs to be. That's what we want to do. We want to now find a solution that will describe theta sub d, this angle, in terms of R and zeta. What's R? It's right here, isn't it? E to the minus zeta omega sub nt. Let's write that down. This is now e to the minus zeta omega sub nt, where this is maybe our sigma, our damping ratio. If we take the natural log of both sides, we can get rid of that exponent. So now we have natural log of R is equal to minus zeta omega sub nt. we're given, with the settling time, we're given R effectively, and if we're given the percent overshoot, we're given zeta. So let's solve for what we don't know, which is the product of omega sub n capital T. We don't know that. We are given R and zeta. Omega sub n T then is equal to the natural log of R divided by minus zeta, or minus natural log of R over zeta. What's our formula for theta sub d? It's right here, isn't it? Omega sub nt square root of 1 minus zeta squared. So if we use that, theta sub d is now omega sub dt, which is omega sub n square root of 1 minus zeta squared t. That's now omega sub nt square root of 1 minus zeta squared. Now we can replace omega sub nt with what we just expressed it in terms of R and zeta. Theta sub d is now minus natural log of R over zeta square root of 1 minus zeta squared. In terms of R, which is settling time, and zeta, percent overshoot, we've now found an expression for our angle. And now if I give you R and the angle, it's easier to draw. You can get out your protractor and your ruler, measure R with your ruler and the angle with your protractor, and now you have the Z delta locations. There's the theta sub d, and this was given. Where theta sub d was derived. We have one more performance spec. We've talked about settling time, percent overshoot. Now let's talk about peak time, or time to peak. How quick does our system get up to its first maximum when we excite it with a constant? I might call that time to peak, or peak time. And last time we said in the continuous time case, time to peak was pi over omega sub d. Do you remember what omega sub d represents in the S-plane? Omega sub d was the imaginary component of our complex pole. Or we've now been doing this even more parameterized. That way. But here, if time to peak is pi over omega sub d, we could actually solve this for omega sub d and obtain pi over t sub p. So if somebody gives you the time to peak in seconds, you can figure out what's the imaginary component of those complex pole pairs. You can find omega sub d. It's just pi divided by time to peak. what shape does omega sub d translate into? If you now had poles at minus sigma plus j omega sub d, and you fixed omega sub d and you varied sigma, what kind of a shape would that produce in the S-plane? Vertical or horizontal? We're fixing omega sub d, and we're varying sigma. What's omega sub d doing? If I gave you a point here, what's this distance? That's sigma, and what's this distance? Omega d. If I fix omega d and I vary sigma, what kind of a line is that producing? Horizontal or vertical? Horizontal, isn't it? So now let's say that this is some line. We'll call it j omega d1, and let's call this line j omega sub d2. If we map that into the z-plane, if we map this blue line over into the z-plane, we're now walking further into the left half plane. We're increasing the damping, and if we increase the damping in the z-plane, what's that doing to some shape in the z-plane? Don't know how to ask this. What happens when we change sigma in the S-plane? What does that do for us in the z-plane? We have e to the minus sigma t, and if we change sigma, we're expanding and contracting a circle, aren't we? So we're changing our radial distance from the origin. What's that look like then in terms of a shape over here? Now for a given, if we looked at e to the j omega sub d1t, that's the angle, and the other piece is this e to the minus sigma t, and that we're varying. That's the r. R times this. And we're fixing omega sub d1, we're fixing t, so that omega sub d1t is really giving us this angle, theta sub d1, which is omega sub d1t. And sigma now makes us move in and out along that angle. We're now varying that, but we now have e to the j omega sub d2t. Where does that live on the z-plane relative to this blue line that we've drawn in the z-plane? Omega sub d2 is related to omega sub d1 in what way? Is it bigger or smaller? Omega sub d2 is blank than omega sub d1. Bigger. Here, t is staying the same, so what's this angle associated with omega sub d2t relative to the angle associated with omega sub d1t? It's bigger, isn't it? So now we can draw relative theta sub d sub 2 is bigger now than than theta sub d sub 1. Let's look at an example. Suppose somebody says that the time to peak is given in number of samples, and let's say it's 6 sample periods. That is, or i.e., time to peak is 6t. Maybe they're not telling us what t is. We now want to find theta sub d. Theta sub d is omega sub dt. And what's omega sub d? Omega sub d is pi over time to peak. And somebody just specified that our time to peak is 6 samples. Or now theta sub d is pi over 6. And what's pi in degrees? If we can't see pi over 6 as an angle, what's pi in degrees? 180. So this theta sub d, if somebody says we want to peak in 6 samples, they're really telling us that they want us to experience 30 degrees each sample. And now that theta sub d would be 30 degrees for whatever the r happens to be. That now locates our z delta in terms of its angle. We know it's at 30 degrees. We can also use this theta sub d one more way. The units on theta sub d is either radians per sample or degrees per sample, depending on what we want to be thinking of. What that angle is, theta sub d, what it represents, it can influence the number of samples per, let me say, oscillation cycle. Suppose we're given theta sub d as 60 degrees per sample. That's a pretty big angle in the z-plane. And remember, a way to connect that with the natural frequency. We can remember that theta sub d is omega sub d t. where omega sub d might have units of radians per second. T is seconds per sample. So here we have radians per second times T, which is seconds per sample, so that the units on theta sub d is radians per sample. Or degrees per sample, depending on how we want to think. Suppose now theta sub d is 60. N, whatever that represents, N we're saying is samples per cycle, is we have 360 degrees per cycle. For every oscillation cycle, we have 360 degrees. So this is now degrees per cycle divided by theta sub d, which is or we could say that that's 2 pi radians per cycle divided by what was theta sub d. If it's 60 degrees, how many, what is that in pi units? Pi over 3 and we said that this was 60. So now we have 360 divided by 60, or 2 divided by 1/3. We now have 6 samples per cycle for N. That's what this theta sub d represents. What's the picture? Let me see if I can sketch this. Suppose that we now had some waveform that looks like that, a decaying exponential, an exponentially damped oscillation. That's what I should have said, an exponentially damped oscillation. What we're saying with n equal to 6 is that if I could do this properly, we're now sampling this six times, 1, 2, 3, 4, 5, 6, for each cycle of oscillation. Our oscillation cycle is the period of that let's call it t sub 0. That's the waveform's period. And that's one oscillation cycle. And we now are specifying 6 samples in that waveform. What do we like to sample in this class? What did we sort of say a rule of thumb might be for the highest frequency? If I now gave you a high frequency, how many times did we want to sample in that particular waveform? 30, wasn't it? So here we're saying 6, but we would really like 30 samples per cycle. So we have a pretty small angle, theta sub d, that we're talking about. But this is just to illustrate the concept. So if you look at this product of n sub d times theta sub d, that's going to be either 360 degrees or 2 pi. That's another way of thinking about it, where n is this number of samples per cycle unit-wise, and theta sub d is either radians per sample or degrees per sample. Or it's so that here we have radians per cycle, or 360 degrees per cycle. That's this n sub d theta sub d. If somebody gives you a particular number of samples per cycle, then they're really specifying theta sub d, the angle. Theta sub d is now 2 pi over n sub d. Or theta sub d is now 360 degrees over n sub d for degrees per sample. If somebody gives you, I want 10 samples per cycle, you can translate that into a theta sub d. That's 2 pi over n sub d, which is 10, or it's now 36 degrees per sample, or 6.28 divided by 10, or 0.628 radians per degree. Let's see if we can summarize what we've done in the time remaining. I'm getting not very far fast. So here we have 3 performance specifications: settling time, percent overshoot, and peak time. Here are the different ways that we can think about those. Settling time, we're thinking geometric shape in the z-plane as circles. If somebody gives you the settling time, either in absolute time or in just number of samples, you can figure out the radius of your dominant poles. If they give you R, you can figure out how long it will take to settle in number of samples from that expression. Percent overshoot, you're thinking hearts, logarithmic spirals in the z-plane. If somebody gives you percent overshoot, you can use this to calculate zeta. Or you could just have a curve that relates percent overshoot and zeta on your crib sheet, and you could then eyeball for different values of percent overshoot what the zeta value is equal to without having to plug in all of those numbers to that equation or into that formula. Or if somebody gives you a zeta, if they say zeta is 0.7, then you can say, oh, my percent overshoot, and what should you calculate? Do you remember? What is the percent overshoot for a zeta of a pure two-pole system in continuous time? If zeta is 0.7, what's the percent overshoot? 5%. If zeta is 0.6, it's about 10% overshoot. Peak time. Now we're thinking angles, theta sub d's. If somebody gives you, and so now time to peak is pi over omega sub d, and so you can see this connection between the imaginary component in the S-plane of your closed loop poles and the time to peak. If you want a smaller time to peak, what does that translate into in terms of your imaginary component? If you want to make T sub p small, what do you do? Pi is fixed. Pi is 3.14. What do you do for omega sub d? If you want T sub p smaller, if you want to shrink, or if you're shrinking T sub p, what are you doing to your system? If you're shrinking T sub p, are you making your system response faster or slower? If you're making the time to peak smaller, if it takes you less time to get to the first peak, you're making your system much faster, aren't you? If it takes a short amount of time to get to that first peak, you're quick. It's fast. And if you want a small T sub p, a fast system, what are you doing with omega sub d? Making it bigger because it's in the denominator of that expression. So pi over a bigger number makes T sub p small, and that makes your system fast. If you have a fast system, you have a big omega sub d. Likewise, if somebody now gives you time to peak in the number of sample periods, n sub p, if they say, I want you to peak in very few samples, they're saying, oh, theta sub d needs to be pretty big. That may not be such a good thing. You may want to decrease your sample period, capital T, and then make your theta sub d smaller. Just saying. But here are the relationships. You can either be given n sub p and calculate theta sub d, or you could be given theta sub d and calculate the time to peak, either in absolute sense or in terms of sample periods. Now, can I make it even more complicated? What in the world? Here I'm trying to give you pairwise combination of performance specs. If somebody gives you a settling time spec and a percent overshoot spec, you can use this first row to calculate R and theta sub d to get your dominant pole locations. If somebody gives you the settling time and the time to peak, boom, they've immediately given you Z delta. They've given you R and theta sub d, and you can calculate those dominant poles. If they give you percent overshoot and time to peak, then we have derived this connection with our zeta and theta sub d with R. So now we can calculate the radius, and we were given theta sub d. Now we have that. The variation on this is, what if we're given all three design specs? Then we may have to adjust one or the other so that they all become compatible. And that's where we will maybe want to give you another lecture for on your own time, since you told me at the beginning of class you have plenty of free time to worry about this class. But hopefully now you have a little bit better understanding of translating performance specs or design specs into Z-plane pole locations. What shapes do we want to be thinking about as you're sleeping tonight? Hearts, circles, and angles. And those correspond to percent overshoot. So now if you wake up in the middle of the night and go hearts, somebody might hear you and you'll say, oh, I was just dreaming about percent overshoot, right? So think about that between now and the next time we meet, and we'll pick up with designing controllers now that we know how to pick pole locations.